So we have last time I think I had derived the formula for finding out axial deformation, axial displacement as we call. Deformation, I cannot compute deformation, I can only see deformation, okay. I can compute displacement of a point, okay. So body gets, or the rod gets deformed, it gets lengthened or compressed, and then we will find out the displacement of a particular point, and for that we got that delta equal to integral p dx by AE, p dx by AE. That was a general formula. And now if p is constant over the, so it comes out of the integral signs. If a is constant, that also comes out of integral sign. E is constant, that also. So you have only dx integral, so dx becomes L. So for a rod subjected to constant force, either compression or tension, the displacement of this rod will be PL by AE. Now this is a very important formula that each one of you should know it by heart. It is not to be forgotten. You don't have to refer to your notes or book that delta equal to PL by AE for any rod which is subjected to a force P or a compressive force P. So either a tension, normally we show tension by a sign plus. Yes, Mr. Sharma. No talking now. So we show it by tension is by a sign plus, and if it is compression, so we show it by. So this rod will undergo a elongation. Of course, the boundary condition is not fixed, so it will. I cannot say that one end will be fixed. So this will be, and then this rod will be under compression. This will become something like this. So shortening or lengthening of the rod delta, so delta will be plus or minus, it will be PL by A. Plus means extension, minus means, so this is a famous formula, and this is a very important formula. This is the first formula that I am saying that you must remember. Now P by delta, that means what is P by delta? Have I been writing delta like this or del? P by delta equal to A by L, and delta by P is equal to L by A inverse. Now I define two quantities which are very again important. You must have this idea. That is, for a unit, if delta equal to unit, that means then P is equal to A by L. If delta equal to unit, then P equal to A by L, and here if P is equal to unit, if I apply a unit force, then delta is equal to L by A. So this gives us the basic definition of what is we call stiffness and flexibility. So the rod undergoes a deflection under unit force. Apply a unit force, the amount of displacement that undergoes is a measure of its flexibility, how flexible this rod is. More displacement, more flexible. Less displacement, less flexible. So this we call flexibility. So this gives us the concept of flexibility. And this gives us with the inverse. That means the force required to produce unit displacement. Here displacement required due to or displacement produced, don't say required, displacement produced due to unit force P, that we call flexibility. So this is the flexibility of the rod. L by AE is called flexibility of the rod. Flexibility of the rod. While the other one, here I have a rod and I want to find out what is the force required to produce unit displacement. So here I will use the word produce. Required or force required. Force required to produce unit, what is that? Unit displacement. This is a measure of stiffness. So this we call stiffness. So stiffness of the rod is stiffness, and stiffness is inverse of flexibility. So stiffness is denoted by a letter K, just like stiffness of the spring is denoted by a letter K, is it not? Small k, not capital K. This, by the way, this is lower case, small k, is stiffness of rod, and that is equal to PL, not P, A by L. And flexibility we denote by a letter small again, F, is the flexibility of the rod. Flexibility of the rod. Flexibility of the rod is L by A. So K is 1 by F. Force required, and if you take how stiff is this body, how stiff is this rod. So I will say what is the force required to give me unit displacement. So there are 10 rods, you do that, find out the forces required. So the maximum force, the rod which takes maximum force will be most stiff, and the inverse will be the flexibility. Okay, so this is what we should you should remember, because we will be using these concepts later. I think I will use now only. I will introduce something very important little later, which has become popular. So this is 283. Now we will yes, last time I had solved a problem, a simple rod which was constrained at one end and of different cross sections, and some forces were applied, and I told you it is very easy to find out the total displacement or any point, because displacement will be summation of each individual parts. So even if the parts were having different cross sections or different lengths, it is possible to find out for each, and every part was subjected to the same force, is it not? Because it is transmitted to the entire length of the rod. Such problems were statically determinate. Why it was statically? So I had taken what is called statically determinate problem. That problem was statically determinate. My problem like this, I told you. This I had fixed, and then I said, okay, let us apply a force here, a force here. So this is P2, this is P1. Please find out the displacement, how much displacement this undergoes. This was L1, this was A1, this is L2, and this is A2. So the displacement, total displacement, it is also denoted by another letter. Delta is also written like this, delta. Both are called delta. This is a capital delta. Okay, I will agree with you. So, both are, these are all Greek letters. Greeks were very advanced in mathematics, you know. We were also advanced in algebra and arithmetic. You see, go through the website and look for one mathematician of the yesteryear. His name is Dr. Ganesh Prasad, Ganesh, Ganesh Prasad, and see his history, Prasad. I would like to just search, you know, whether something is there on the internet about him. He was a great mathematician of yesteryears, of course about 100 years ago, and he did a lot of work. And plus, of course, we have Aryabhat, yes, Ramanujam, great mathematician, yes. So our history is very rich, but only thing in the last 100 years we have not produced any great mathematician. Who? So try to, I think we should have someone, you know, because in the last, no, I think it has been free of any. So same thing. We had very good scientists, you know, because history of engineering is very new. Engineering started, you know, with the first school in Roorkee, which was and that was about 160 years ago. That was the first school, Thomsonian. It used to be called, it was a polytechnic, and that started. So we were not very much behind the Americans. See, the first school, engineering school, started only in 1906 in USA. But Britain was much ahead of us. France was still ahead of us. They had very good schools right from 16th century, you know. 1600, 1500 they had. So they had, okay. So this is about, so engineering we have just begun after independence, because there was no concept of engineering scientist or engineer. You know, engineer was considered to be a hardware person. Hardware, that is, you do something in the field, not something in the not invent something which is of scientific value. But now engineers, mathematicians, physicists, I think they all do similar type of work. So okay, this is delta, and this is which can also be written as I equal to this. But then this was statically determinate. Why was it this is statically determinate? See, if you draw the free body diagram, Okay, who will answer this? Why it is statically determinate? There is some reaction. Yes, this is what is the free body diagram. I don't know the direction of R1, so I have drawn everything positive in the positive x direction. This is x direction, so everything is positive in positive x direction. I have taken all the forces. So I can find out R1 here. The unknown force, unknown reaction that is there at the support, I can write equilibrium R1 plus P1 plus P2 equal to 0. Therefore, this gives me R1 equal to minus P1 plus P2. So clearly, this tells us that the direction that I have chosen originally is not right. An actual direction is like this. So you have P2 here, you have P1 here, and at this point, in order to keep this rod in equilibrium, you have P1 plus P2 here. They should be acting here. So this is the solution. You could solve for solution. You could get the value of the solution by writing the condition of equilibrium. So what you have written down is condition of equilibrium. So this alone was enough to find out the unknown. Such problems where you can find out all the unknowns in the problem just by making use of the conditions of equilibrium are called statically determinate. So one class of problem will be statically determinate. Hey, this is whatever I have written is right or wrong? Wrong, yes. See, this is okay. Here, P2 at any cross section will be P2. What about here? Yes. So P2, here it will be P2 also. So this is not right. So here, anyway, Pi means you have to find out. I will use here word Fi. Let me use the letter Fi. Fi means the force in the particular rod. So you should have spoken. If you saw that I was making a small mistake. So in this section it is P1 plus P2. There it is P1. There it is P2. Okay. So I think we have done statically determinate, and you should be able to solve any statically determinate problem without any difficulty. Now let us talk of some problem which is not so and which is of this type. Okay, so this is, now let's take a example of this type. We have a So I have two sections of rod, two lengths of rod whose length is given as let us call this as L1. See, please do not talk when you are in the class. This is A1, this is A2. So this is the geometry, it is fixed at point A. and C, this is B. This point is B. Now we have applied here, let us say in the center of this, I have applied a force P1. In the center of this, I have applied a force P2. Now both are constrained. So free body diagram. How to draw free body diagram? Isolate the body from its surrounding. This is the basic, that is what people say. Isolate, remove the support. So remove the support means you must be very good in drawing free body diagram. Unless you are able to draw free body diagrams correctly, you will not be able to solve any problem. So these are the acting forces P1, P2. Now you have also, because it is being pulled down, so there will be some reaction at this support. I have cut it here. Free body diagram means I have cut it here and I have cut it here, removed from the support. So the support will offer some resistance. So reaction has to be given. So let us call this as RA, and at this point RB. Generally, sorry, RC, if it is C here. Point C, so let us call this at reaction at C, a reaction at, just a minute, let me just adjust the slide. Okay, so now you have so if you write the vertical equilibrium, this rod is in equilibrium, so I write down the condition of equilibrium. So I get here, everything is, let us call everything is positive in the positive one direction, that is downwards from top to bottom. So you will have RA plus P1 plus P2 plus RC equal to 0. Is there any other equation that I can write? How many equations of equilibrium this problem has for one dimensional loads are acting in one direction? One, only one condition. So I have written, and how many unknowns are there? So unknowns, 2, equilibrium equations, 1. So 2 is greater than 1, 2 minus 1. So this 1 extra, it has, we say that it is indeterminate of degree 1. This problem we cannot solve. I need one more condition. I need one more equation involving R1 and R2, I mean RA and RC, then only I can solve. So this is statically, why it is called statically? I mean, of course, normally we drop statically, but actual one is statically indeterminate. Statically indeterminate of degree 1. I need one extra equation. And if you recall, in the first lecture I had told you that there are 3 basic principles of solid mechanics for deformable body. One is equilibrium. Second one, you must study deformation of the body. because this is not rigid body like the first course. It is not the engineering course, engineering mechanics course. In the first course, you studied only about mechanics of rigid bodies. Bodies were at rest, but then the body was rigid. What is difference between, how do you define a rigid body? Huh? Yes? What is this? Strain? Distance is constant. Okay. Is it okay? That is how you define rigid body? Of course. Yes, it is all right. You can write it in different ways. You can express this, it does not change. Distance between any 2 points remains invariant. It does not change. It remains constant. These are the various phrases that one can use. But it does not happen in a deformable body. We are studying mechanics of deformable body, not rigid body now. We are graduating. We have graduated from rigid body to deformable body. So here we must study also deformation. How does the body deform? And once you study deformation, then I told you there is also one associated law. Then the material comes in the picture. What is the material of which this body is made of? And that has its own relationship between stress and strain. So you study deformation, it's all right. Then you also should know the law which governs stress-strain variation. The law relating stress to strain, that is called generalized Hooke's law or simple Hooke's law you are talking of. I think I have already spoken something about it. So there are three principles, that is, one is equilibrium, second one is study of deformation, and in study of deformation you study, then you define strains, then you relate strains to displacement, and third one is from forces at any cross section you get stresses, and from deformation you have got strains. So they have to be related for the particular material. So stress-strain relationship. So the third principle is what is it is also called constitutive relation of the material. Constitutive, TIVE, constitutive relation. Instead of calling stress-strain relation, what is the constitutive relation of the material? So these are the three basic principles. So we will have to make use of these three principles in order to solve. And of course, you must consider in the process what? Anyone? Sharmaji? What do you consider? In addition to three principles, equilibrium, deformation or stress-strain relation, and then third one is stress-strain, and third one is relationship between strain displacement relation. Deformation means strain displacement relation, and third one is relate stress to strain. Okay, so these are the three basic principles, and then that has to be used in conjunction with what? The problem. What is the problem? Problem must have, any problem in reality must have, this is a body, a rod. So okay, then what? Do you have to say anything about this rod? How will you get stresses? Geometry of the body? No. Material has already come in stress-strain relationship. Constraints, yes. You first, before you can apply force or load to a body, it must be constrained. What is constraint called in terms of mathematics or in mathematical language? Boundary conditions. You must fix the boundaries. Unless I fix this, how can you apply a force? Fix the body in space. Otherwise this will be moving in space. You apply a force, then it will be moving. It has to be fixed in space. So fix its coordinates. That is called boundary conditions. Just like this body has got boundary conditions, but then it has been fixed more than necessary. You needed only one end to be fixed, then it was a statically determinate problem. But then I have fixed more, extra fixity. Now it has become indeterminate. So boundary conditions. The boundary condition is extremely important. Without boundary condition, without constraints, you cannot solve, you cannot begin the solution of a problem. And then mathematically all these three equations and boundary condition, mathematically it is called a boundary value problem. BVP, write it down. BVP in short, boundary value problem. So okay, so this is now what to do about this. So you have got this. So what should we do? We have to now let me first, the rule or the procedure for solving any indeterminate problem is make the problem determinate first. Get rid of that extra constraint. So I will just keep it so this problem, I have removed the bottom boundary condition. This was the boundary, it was at A and C. So I have removed it, made it determinate. So this is now my A, and this is B, this is C, and this is P1, and this is P2. This is determinate. So because I can solve a determinate problem. I can solve a determinate problem, but that is not the real problem. But yes, I can solve it. So then what I will do, I will solve it. And if you solve the determinate problem, then what will happen? This rod will elongate. This will come here. This point also will come here. And there will be some. So there is this delta, call this as delta naught. This will undergo a displacement delta naught, but I don't want delta naught. How did you get delta naught? But delta naught can be found out very simply, because delta naught will be equal to, if this is L2, A2, and this is A1 and L1. So delta naught will be, see, at any cross section here from C to B, the cross section is subjected to free body diagram. Up to point B. So you have center, and if I cut it above this, let us say, this is center. So first let us say if you cut it here, then what is the, yes, what is the force that is being applied here? Is there any, if I take section this, this bottom portion from the center of this BC to C, is there any force that is acting or which is there in the body? Free body diagram, you see, if you cut it, there is no force below. We are using this is a weightless rod. The rod material, we are not taking the self weight or the density of the material. So P is applied only at the center. Is it okay? So one good thing is P is applied only. So up to center, there is no force. Now if I take any cross section, that means over here, so over here, it is like this. This is center. This is P2. So here it has to be P2. And that P2 will be going up to which section? Any cross section that I take up to the center of this top one, the bottom portion. See, you must understand this. I am cutting this, drawing the free body diagram of this now up to here, up to a point just below this where this load is applied. So that means I am taking it the other day. Who jumped and opened the door of our one of you helped us in opening the door which had been locked from inside in the department. He is not there in the class, and his friend, two of you were there. Huh? You were there? No. You did not jump. You know, he was so quick. And he said, sir, I will jump and I will go into through the window and then I will open the door from inside. Very good. And he did it. Hardly it took 1 minute, you know, for him. So, okay. So this is P2. P2 is applied in the center of this bottom. P2 is applied in the center. Now I have taken a section up to here. So this cross section, if you draw this free body diagram, so this will be subjected to P2 top. That means from this point to this point, the rod is subjected to P2. From here to here, so let us call now distances. It should be very clear that let us call this A, B, C, and then this, let us say D, and this is E. So from C to D no force. Do you all agree that there is no force from C to D? Then from D to E, force is only P2 force. Every cross section is subjected only to P2 force. From D to E, yes, E is here, yes, up to here. From D, that means in the bigger cross section as well as in the smaller cross section, the force that will be acting will be only P2. Then you take a section above, cross that. So learn how to draw free body diagram. So there is a force here P2 in the center of this, and then here there is a force P1. So then at this cross section over here, I am drawing now this section. At this cross section, what will be the force? Understand, this is, if you don't understand now, you will never be able to understand. So from here to, from E to A, every cross section is subjected to how much force? P1 plus P2. From here to here, this one is subjected to P1 plus P2. Then from here to here, this is all 0. And from here to here, it is P2. So can you not find out what will be the displacement delta naught? Delta naught will be what? I will stop after finding out delta naught. Just wait for 1 minute. So what is the delta naught? Start from anyway from C to D. There is no force, so this will be just coming down as a rigid body. Then from D to B, cross section is different. D to B, cross section is different. The length is how much? D to B, L2 by 2. So D to B. So force in, shall I write D to B into L by 2, L2 by 2, L2 by 2 divided by how much? A2 by, let us say it is E2. Modulus of elasticity also is changing. So that gives me the displacement because of this, from here to here. Then from here to here, plus force in B to E into L1 by 2 divided by A1 into E1. So this covers this much. Because the cross section is changing, so you must take differently. Because cross section is changing, we have taken it like this. So first portion is 0, from here to here it is 0, and plus how much? Now you are left with EA. So force in EA. Is it okay? Force in this length, E to A. How much is the force? What that you know already. It is P1 plus P2. But then that multiplied by L1 by 2 divided by area of cross section, which is A1 into E1. So summation of these three will give you, and then this FBD is how much, please? FBD is P2. What is FBE? FB is how much? FBE. B to E is again P2. And what is FEA? Equal to P1 plus P2. So can you not find out 0 delta naught now? But then this is a part of the problem. We have made the problem determinate. So I have got additional. Now the real solution will be obtained when you try to push it back such that find out the reaction, because at this support there was a reaction, bottom support, that is RC. RC is there. So push it in such a way that produces a displacement equal to delta naught. Then I will get the proper reaction. And that will be called what? That condition. So this is the first. It is a 0, when you make the problem determinate. So always make the problem determinate, find out the displacement. Then now you put only the reaction. So next problem, of course, it is, I don't want to, but then we will start from here next time, that is on now Tuesday.